Carl is our next K9LA, our next instructor, and you're gonna learn some things about propagation. Probably one of the best knowledgeable people on propagation. So gonna make you all experts.
All right, thank you, Bob. Well, I'm Carl, K9LA from Fort Wayne, Indiana. Question already? No. Yep. Oh. Okay, sounds good. My wife is here, Vicky, AE9YL. And like I said, we're from Fort Wayne, which is up in the northeast corner next to Michigan and Ohio. And we're really glad to be here. We've had two great presentations. Now you're stuck with me. Oh, well, that's the way it goes. So good afternoon to everyone, especially Maggie. We're very fond of animals. We've had dogs, and right now we got 8 cats at home. So that's great, but that's a lot of fun. So let's get started here. We'll talk about propagation. Let's see here. There it is. Okay, let's see what this does. I don't know. That probably works. Yeah, there we go. So here's the agenda. We're going to talk about cycle 25, give an update. And the two big things are, is it in its decline? And is it going to have 2 peaks? So we'll get into that. Then we'll talk about some basic propagation issues. Of course, I'll be open for questions later. Anything you want to ask, because I can't cover everything in 45 minutes. Using space weather to predict propagation, we'll go over that a little bit. And then what can we expect for the end of this year and also in 2026? And I'll do that by the bands. And I'll talk about some antennas too. I know they've been talked about already, but I'll get in a little bit deeper. Basically looking at, well, if you're starting to DX, what kind of antennas, and then how do you move up as you want to work more people. And one thing I want to say about being a DXer, you're going to learn a lot about geography, and you're going to learn quite a bit about politics too, because remember, the entities are geopolitical. So it's a great way to learn about the world, that's for sure. Okay, cycle 25 update. Here we go. On the left is a plot of all the previous 24 solar cycles, the maximum smooth sunspot number they hit. Now, what you can see is it's very cyclic in nature. We've been through 3 periods of big solar cycles and 2 periods of smaller solar cycles. And what it looks like right now is that cycle 24, that one all the way on the right, has ushered us into a 3rd period of small solar cycles. Now, I can see, just looking at the audience, for most of us that probably doesn't mean too much because we may not be around for this 3rd period of small solar cycles, but well, we'll see what happens. Okay, there's some people planning on it, but we'll have to see. So I took a shot at making a prediction for cycle 25 back when we were experiencing solar minimum between 24 and 25. That was, December 2019 or so. And what I did is looked at how long we were at solar minimum and how big was the next solar cycle. We had quite a bit of data looking at that. And I plotted a scatter diagram of how many months were at solar minimum. And I used a smooth sunspot number less than or equal to 20. And how big was the next cycle? And you can see that there is an obvious trend. the longer we spend at solar minimum, the smaller the next cycle is. So based on that, we were at solar min for about 39 months. And if we put that on, put that on that trend line, that red trend line, it said that cycle 25 would be around 140. So that was my prediction back in 2019. Well, cycle 25 is at least about 160. So, yeah, don't count on me for any predictions for cycle 26, okay? The sun's going to do what it wants to do, not what we think it should do. There we go. So here's cycle 26. It's the thick red line. That's not cycle 26, 25 update. The thick red line is cycle 25, and you can see that it went up and it peaked, it looks like, and it looks like it's starting to come down. Now, there are 3 other solar cycles on there, 4 other solar cycles. The one at the bottom, green, that's cycle 24. Just as a reminder, 24 was the smallest in our lifetimes and the 4th smallest in recorded history. So 24 was kind of small. The one above the red, cycle 25, is cycle 23. If you take an average of all the 24 previous solar cycles, cycle 23 was pretty much right about at the average of that. And then, of course, there was cycle 21 and peaked in 79. It was moderately big. It's too bad we didn't have HF rigs with 6 meters on it back then. It would have been really a lot of fun. And of course, the largest solar cycle in recorded history is cycle 19, peaked in, I think it was March of 58, I believe, something like that. How many were on for that? Anybody? No? Okay. Oh, darn. Yeah, I got my novice in October 61, so I was on the decline of cycle 19. So, whew, wow. So, will it reach or exceed an average cycle like 23? Well, right now it doesn't look like it. It's kind of stuck between a small cycle and an average cycle. Like I say at the bottom there, I just don't think it's going to get up to an average cycle, so we're kind of stuck with that. Now, I talked about smooth sunspot numbers, right? That's the official measurement of a solar cycle, a smooth sunspot number. So what is a smooth sunspot number? Here's cycle 23, and there are three curves that are plotted on that. The first is the daily sunspot number. That's in red, and it's very spiky. So it'd be hard to tell what's going on in a solar cycle if you just looked at daily data. So how do you get rid of all those spikes? Well, you do some averaging. So let's look at the monthly mean or the monthly average values for cycle 23, and that's what the blue is. You can still see some spikes in there, and it's still a little bit difficult to see what's going on. So what do you do about that? You further average. And that's what the smooth sunspot number is. It's a 12-month running average of monthly average sunspot numbers. And you can see why they call it smooth. That's the green line. It's very smooth. It's obvious cycle 23 had a 2 peaks. It peaked and had a nice valley, and then it went up again. And like I said, the smooth sunspot number is how we officially measure solar cycles, so we're kind of stuck with it. And the other thing is the smooth sunspot number correlates to propagation, the best correlation that we have at the moment. we don't have daily predictions, and I'll get into that a little bit later when we talk about space weather. And that's what all of our propagation programs, BOACAP, W6EL prop, whatever else is out there, it requires a smooth sunspot number for the given month. And from that, it tells us the monthly median MUF and signal strength, median implying 50% probability. So right now, because we don't understand everything enough, we have a statistical propagation predictions. We'll get into that a little bit later too. So here's an interesting website that I just kind of like to look at every once in a while. It's a year's worth of data. And the URL for that's up there at the top, solen.info/solar. Like I said, that's a year's worth of data. The one I pulled is from October 7th of 2024 to September 15th of 2025. And what's kind of obvious, even though there's lots of data in there, there's sunspot number, the daily sunspot number, the daily solar flux, and the AP index. We'll get into the AP index later. You can see that the sunspots and the 10.7 centimeter solar flux have been going down since about mid-2024. So that strongly suggests that cycle 25 is in its decline, but then way at the right, it kind of stopped declining. And what's going to happen after that? Will it go up or will it continue to go down slowly? So are we going to have one or two peaks? And that'll answer the question if cycle 25 is going to continue its decrease or maybe come back up for a little bit. There's a picture of cycle 24 on the left. We're looking at where the sunspots emerge on the solar disk. Okay? In the plot there, the blue is the sunspots that emerged in the northern solar hemisphere. Oranges are the sunspots that emerged in the southern solar hemisphere. And you can see what happened in cycle 24. Initially, the northern solar hemisphere was very active. The southern solar hemisphere wasn't. But then a little bit later, it flipped. The southern solar hemisphere was very active, but the northern solar hemisphere was not very active. And that's what gave us the two peaks of cycle 24. And if I look at 23, probably the same thing. And I think 22 had two peaks also. The green is just the total of both the northern and southern. So if we go to cycle 25, initially both solar hemispheres were pretty much equal. But then the past several months, the northern hemisphere has kind of quieted down. The southern solar hemisphere had a peak, but it looks like it's coming down. All we can do is kind of wait and see what happens. I kind of think that we're not going to have a second peak, that we're in the decline of cycle 25, which could be good or bad, depending on your operating habits. Come on, there we go. So there's the prediction from NOAA for cycle 25. Now you got to remember that their initial prediction for cycle 25 was quite low, and cycle 25 beat that. So take this with a grain of salt. You can see where we are there in 2025, and their prediction says we should be going down, and that's about it. Now I annotated on there when 10 meters may start dropping out. So just because we're in the decline doesn't mean we're going to lose the higher HF bands. That's because cycle 25 was kind of big enough to keep those bands open for a little bit longer. And we'll talk about that when we look at the forecast for what's going to happen in for the end of this year and also 2026. Okay, some propagation issues. What starts propagation? Well, the sun's the big factor here. It emits electromagnetic radiation at many wavelengths, from very, very short, X-rays, gamma rays, to very, very long radio wave. You can listen to Jupiter on 21 megahertz. Okay, so that says the sun can also emit radiation at radio wavelengths. Of course, the visible light is where the most radiation from the sun comes from, or at those wavelengths from 400 to 700 nanometers. That's pretty short. The important range of radiation for our amateur bands is very short wavelengths. That's way over on the left. And they're called ionizing wavelengths because that's what they do. They ionize the atmosphere. Notice where 10.7 centimeter solar flux is. It's nowhere near ionizing wavelengths. So just remember that 10.7 centimeter solar flux basically couldn't ionize its way out of a paper bag. So just remember that. Solar flux and also sunspots are really just proxies for the really true ionizing radiation, which is extreme ultraviolet for the F2 region and X-rays for the D and E region. And the ionosphere, this is what happens when the sun's radiation hits our atmosphere. Depending on the wavelength of the radiation and the concentration of the species in the atmosphere, oxygen, nitrogen, and all that stuff, it creates different layers of the ionosphere. The one that's most important to us is the F2 region. It's highest, which means it gives us the longest hops. And it's caused by the extreme ultraviolet radiation from the sun. The longer X-ray wavelengths give us the E region, shorter X-rays, and also Lyman alpha spectral line of hydrogen result in the D region. And there's a picture on the right. It says, during the daytime we have F2, F1, E, and D, but at nighttime we basically have just E and F region, F1 and F2 kind of combined. But the important one, like I mentioned for most of us, even not just DXers, is the F2 region because it's the highest up there and gives us the longest hops. Here's a typical solar cycle. On average, the rise time of a typical solar cycle is about 4 years. The average descent time or the decline is about 7 years. So 4 plus 7, that's what a solar cycle is, about 11 years. Some are a little bit shorter, some are a little bit longer. But on average, it's about 11 years and 4 years to get up and 7 years to get down. Now, the higher HF bands are best at solar maximum. I think we probably all know that because that's when the sun's putting out lots of extreme ultraviolet radiation. And it includes 6 meters too, 15, 12, 10, and 6 meters. And the lower bands are in 160 are best at solar minimum because that's the least amount of ionospheric absorption. So, if you're a 160 meter aficionado, you'd prefer solar minimum to being a high HF band aficionado that prefers solar maximum. A lot of DX can be worked at solar maximum on 160. I remember W8JI. He worked over 200 countries in all 40 zones around the maximum of solar cycle 23. So it's what Bill kind of said is keep your butt in a chair and you probably work a lot of stuff. Now, one of the interesting issues with solar maximum is we have to take the bad with the good. The good, of course, is lots of radiation for the sun to make propagation on 15, 12, 10 meters, and even 6 meters good. But what's the bad? It's the disturbances to propagation. And these affect the F2 region in not a good way. There are 3 disturbances to propagation. Geomagnetic storms. Probably you're most familiar with CMEs, coronal mass ejections. They send lots of junk towards us, and it can screw up the F2 region for days. We can tell because the K indices are very elevated when this happens. And we'll get into the K and A and some other stuff here in a bit. Geomagnetic storms. The coronal mass ejections are most prevalent at solar maximum. So that's the bad. Also, coronal holes. We're starting to see a lot of those. They are most prevalent on the declining side of a solar cycle. So once we pass solar maximum, things may not get better for the F2 region, because in general, those coronal holes are worse than the CMEs. Now there's a solar radiation storm. That's when we get some big solar flares, big M's and also X-class solar flares. And those solar radiation storms are most prevalent around solar maximum because that's when big solar flares are most prevalent. Then there's radio blackout. That's also caused by a big solar flare, and it causes increased ionization in the D region on the daylight side of Earth, and the bands, especially the lower bands, can go away for about an hour or two, but they come back. So the quietest period of a solar cycle appears to be when it's in its ascent. So that's a good thing to remember if you're going somewhere. So here's a look at the A index over a solar cycle. The A index is the daily average of the 8 K indices. So it's a kind of a coarse view of what's going on with the Earth's magnetic field. I think that's blue. The blue curve is the 10.7 centimeter solar flux of cycle 24, and you can see the 2 peaks it had. The second peak was much bigger than the first peak. And the red plot is the AP index. It's the daily A index. Now the P after A is just indicating that it's a planetary index. It's not a single observatory. It's trying to get a worldwide view of what the geomagnetic field, the Earth's magnetic field, is doing. And you can see that around solar maximum, the A index peaks, but the A index really peaks even higher most of the time during the decline of a solar cycle. So we're going to see more disturbances to propagation as cycle 25 declines. Nothing we can do about it. But usually there's a silver lining in a dark cloud. And one thing you should do if you see a moderate spike in the K index that doesn't last more than a couple 3-hour periods, take a look at the higher bands. There may be some enhanced propagation, F2 propagation, for a short period of time, which means 15, 12, and 10 may be open, even 6 meters. So let's take a look at that real quick. Here's 2 examples. The top one is the 2018 California QSO party. In fact, the California QSO party is on this weekend. Hopefully I'll get on when we get home on Sunday. You can see that on the left at the top is the MUF of the Boulder ionoson. In other words, if the Boulder ionoson was the midpoint of a 3,000 kilometer path. That's what the maximum usable frequency would be. And you can see up to the day of the contest back in 2018, the MUF was around 20 megahertz. So I didn't work any W6s. But what happened on Sunday of the contest, you can see on the right there, the K indice spiked up to, I think it's about 6 or so, for 3 of the 3-hour periods. And look what happened to the MUF on the left. It went up to above 30 megahertz. Sure enough, I worked a lot of W6s in California on Sunday. On the bottom is some other examples. They're contradictory. The ionosonde in Peru there on the left shows that when the K indices spiked up a little bit at the end of August 5th, back in 2011, that the MUF went down. But at Eglin Air Force Base, when the K indices spiked up on the same day, the MUF shot up. So it's not a sure thing either way, but it's good to check in case the K index spikes up for a couple 3-hour periods. Okay. A little bit more about the K and A indices. Everything starts with the K index. It's a 3-hour index, so there's 8 of them during the day. It tells us how active the Earth's magnetic field is. It's on a logarithmic scale from 0 to 9. 0 is very quiet. 9 is very disturbed. And we're talking about the Earth's magnetic field being quiet or disturbed. And of course, the high K index can indicate a disturbed F2 region and also auroral activity. So who likes high K indices? Well, the VHF guys, right? That's when you'll see auroral propagation. What's the A index? Well, it's the daily average of the 8 K indices. So it's really yesterday's value, which kind of tells you a little bit about what's happening maybe today. It's on a linear scale, goes from 0 to 400. So 0, of course, is quiet. 400 is extremely disturbed. Like I mentioned before, if the K or the A index has a P after it, that's from several observatories around the world to give a more of an average of what's going on throughout the whole world. Back in May of this year, we had some pretty interesting stuff. There was almost 3 or 4 days of K indices above 7. There were solar flares, so that screwed up the bands quite a bit. Okay. The K index, B sub Z, and the solar wind speed, they're all correlated. What's the B sub Z index? Well, that's the component of the sun's magnetic field that is perpendicular to the ecliptic. So what's the ecliptic? That's the plane in which Earth and most of the other planets go around the sun. So being perpendicular to the ecliptic is pretty much a north-south value, which kind of, you know, is kind of what the Earth's magnetic field is, north-south. So when the K index is high, B sub Z is going to be large negative, and the solar wind speed is going to be very high. Quiet time's about 400 kilometers per second. And high K index, large B sub Z, and high solar wind speed says that the sun's magnetic field can couple to the Earth's magnetic field and send us a lot of stuff and really screw up the F2 region. And there's a banner from the QRZ.com. It comes from N0NBH, and he has a lot of data on there. And I highlighted the K index, the BZ, and the solar wind in those yellow boxes. You can take a look at that and get a general idea what's going on. Now, that's looking at what the geomagnetic field is doing. What about ionization parameters? Well, there are 4 parameters on that banner, and they're also in the yellow boxes. There's the MUF-US boulder, which is an indication of what's the MUF over the boulder ionoson. That gives you a good idea what's going on. Unfortunately, that data is not being reported at the time. And it's mostly a political issue. And I'm not sure if it's ever going to get resolved. So that's why in that banner, MUFS boulder, no report. That's the way it goes. But we still have the 304A. That's the extreme ultraviolet radiation from the sun at 30.4 nanometers. We have the SFI, the daily 10.7 centimeter solar flux, and SN, the daily sunspot number. Those are correlated, so when the EUV radiation is high and the SFI is high and sunspot number is high, that means there might be some really good propagation, some F2 propagation. But, of course, it could be disturbed by the fact that the geomagnetic field is active and going to screw up the F2 region. So what do we need in terms of solar flux to open the bands? Here's some general guidelines. For 160 through 17, there's usually enough extreme ultraviolet from the sun, even if we're at solar minimum, to keep those bands open. In other words, they can refract signals back to Earth. Doesn't say anything about what signal level comes out, though. For 15 meters, we need a long-term SFI greater than about 95. When I say long-term, ideally that would be the smooth solar flux, but maybe a monthly average gives you a good idea. For 10 meters, we need the SFI greater than 125 for a long term. And 6 meters, generally 200 for the SFI. Now, if you go over to that N0 NBH banner, you'll see that the flux is 122, I think. Sunspots are 79. So what that says is, no, that's 122. It says that 10 meters is probably going to be open. 6 meters, that's kind of iffy. But it's a good way to determine, you know, where we are and what's going on. From a banner, you can see what's going on. Now, we're coming out of the summer, right? We're into the fall right now. Yeah, we're past fall, September 21, I think it was, or 22. What happens every year is, as we go through the summer months, the MUF decreases. Here's an example from K9LA to, I think, Great Britain. Yeah, to G. And that's the MUF at a daytime for all 12 months. And you can see there's a decreased MUFs from April through August, but then as we move into the fall and winter months, the MUF is going to come up again. And that's caused by just a change in the composition of the atmosphere. It has to do with the ratio of oxygen atoms, which are good for production, ion production. The ratio of oxygen atoms to molecular nitrogen. Molecular nitrogen is good for recombination. It takes the free electrons away. And the MUF goes down during the summer months. We are exiting this summer slump, and this fall and winter we're going to have some pretty good propagation again. Okay, just a quick comment about the digital modes. The digital modes are more effective than CW and sideband. 10 minutes, okay. What makes them better are the fact that when they decode, they can use a very, very narrow decode bandwidth, or an IF bandwidth. So they can less noise will be generated in the receiver or get into the receiver so that they can hear signals that are weaker than like a CW or sideband signal. CW is more effective than sideband, so that's a good idea to learn Morse code, and that's been explained with our Bill and Glenn have talked about that. There's the weak signal to noise limits. You can see that whisper is very good, but of course it takes a while. But that's okay. Okay. So what is the ionosphere doing today? Well, unfortunately, our understanding of propagation is not on a daily basis. Okay? It's really probabilistic, it's statistical with a 50% probability. So if you plug in today's solar flux and today's the K-index right now, that won't tell you exactly what's going on up there. Yeah, give you kind of an idea, but it's still not going to be deterministic like we'd really like to have some propagations that are on a daily basis. We're just not there yet, and that's because there are really three processes that determine how much ionization there are up there. Of course, the solar radiation starts it all. Geomagnetic field activity can screw it up most of the time. And we're also beginning to realize that events in the lower atmosphere or even at ground level, like a hurricane, we can see signatures in the F2 region of the ionosphere, and we don't know enough about that. So we only know kind of two of the three processes very well, and that's what's keeping us from having daily propagations yet. Maybe someday we'll have them. So in my humble opinion, of all those parameters out there, I think you should look at SFI, solar flux, and also the K-index. You can look at them on that QRZ banner from N0NBH. They're at solarham.com, Space Weather Prediction Center, and the Space Weather Woman. I don't know if she talks about them. She probably does in her weekly videos. So the solar flux index will tell you how strong the ionosphere may be. And looking back at slide 20, it said, 15 meters we need this, 10 meters we need this. But the K-index is important. It may tell you that the F2 region really isn't what the solar flux index says it could be, because it could be screwing up the F2 region. In general, we desire a K-index less than or equal to 3. Okay, so the higher HF bands are going to be really good this fall and winter, probably out through 2026 and maybe even early 2027. So if you need to work countries, zones, states, whatever on higher HF bands, now's the time to get on. 6 meters, well, if 6 meters is in its decline, we're not going to see any improvements. We'll still see some 6 meter F2 probably this fall and winter, but it certainly won't be anything like cycle 23, the average cycle. That's the way it goes. On the lower bands, they're best around solar minimum. The problem with the lower bands is, our society is progressing towards more and more electronic devices. So there's definitely more noise, man-made noise out there, which is going to limit us. Also, there's another effect of us putting more and more carbon dioxide into the atmosphere. That could be increasing electrons down at low level, but I'm not too sure about that yet. So low banders are going to have some challenges, that's for sure, even at solar minimum. Yeah, there's that. I won't get into some tennis. Okay, what's your goal? That's really what you should do. Are you just going to have fun working DX? You want to achieve DXCC or worked all zones? You want to get on the honor roll? That's been talked about a lot. You want to get to the top of the honor roll. I was content many years ago, 5 minutes, I was content many years ago that just to get on the honor roll, because I never thought I'd ever work all 340 entities. But one day, 404FN stroke P5 in North Korea showed up, and Vicki and I both worked them. And once I worked him, I said, boy, I only need a handful of others to get to the top. And so I dove in, sat in a chair a lot, kept my butt in the chair, and managed to do it. That was pretty good. As your goals increase, you probably need to put up bigger antennas. You can get to the honor roll with QRP, but you need some big antennas probably. And an amplifier really helps, like an AL 811, 600 watts. That's very convenient. It's also, the AL 811 also works on 160. It's 3 811s in parallel. So usually starting small means an inverted V or vertical, and then you can progress up, and you can just look at all those there on the bands, different bands. It's in the charts there that you have in front of you. 160 dipole or inverted V at 55 feet. You'll work lots of DX, Western Europe, Caribbean, South America. But generally for more than that, you'd probably need a better antenna, like a good inverted L. And of course, the top of the line would be probably a 4-square, which got to have some property for that. So cycle 25 is between a small cycle, 24, and an average cycle, 23. I'm guessing we're only going to have one peak. And a higher HF band should be good for 2025, 2026, and maybe into 2027. And of course, we're going to have more geomagnetic storms, which screw up the F2 region as we're in the decline of cycle 25. Now, I should have mentioned at the beginning, of course I forgot, was Vicki and I have had the good fortune of being on several expeditions. We were in Damascus, Syria, February 2001 at YK9A. She can generate bigger pilots than me. That's the way it goes. Also, in July of 2002, we went to Market Reef, OJ0. We had a great time there. And of course, there was a German lady who worked some cues from Market Reef years ago, but Vicki was the first one, and she spent a lot of time on the radio. Of course, there's not much else to do on Market Reef, but sit and play on a radio, eat, and sleep, I guess. Although it was kind of tough to sleep in July with all the light, so whatever. So that's all I have. Get on higher bands right now and have some fun. And I can try and answer any questions you have. I know I didn't cover a lot of stuff. Gray line propagation that Bill mentioned. It's a very good possibility on long paths. I've never seen a gray line short path enhancement. It's always long path, which means sun rises at one end and sun sets at the other end. So always look for that, because that's going to help. Also, when the path is kind of perpendicular to the terminator, that's when you can see a sunrise enhancement. Like when Europe is at sunrise and we're not, there can be an enhancement. So take advantage of some of those things. That's about it. And I guess we got time for questions, right?
Thanks, Carl.
Sure. Yeah.
Okay.
Okay.
And Vicki, thank you both.
Yes, sir. Right. Okay. Two questions, really. One is the meteor showers. Of course, that's going to be great for VHF type stuff and probably 6 meters. Always listen for meteors during the big showers and see what happens. That's going to be good. The second is volcanoes activity. Yes, I mentioned that events in the lower atmosphere or even at ground level, we can see the signature in the ionosphere of those events. Generally, it affects the ionosphere around the volcano, so it's not a widespread effect, but it can happen, and if your path just happens to be going through the ionosphere above a volcano, you might see a difference, but other than that, it's kind of hard to say that anything else had happened. Yes, it could have. Yes, the volcano could affect air traffic, mostly because of the junk that the volcano puts up, and it gets into their engines, and you don't want to lose your engines. That's for sure. Yes, sir. Okay. What antenna should we be using, specifically polarization, horizontal or vertical, for working DX, really? That's a general question, a good one, too. The advantage of horizontal antennas is twofold. One is generally it doesn't depend on the ground too much, okay? And the second important thing with a horizontal antenna is that it picks up less man-made noise, because most man-made noise is vertical polarized. But if you live in a quiet location, there's no reason why a vertical shouldn't be very acceptable. That's because on HF, when we send our signals up into the ionosphere, it splits into two characteristic waves, the ordinary and the extraordinary. And they're 90 degrees, they're orthogonal, they're 90 degrees out of phase. So a vertical or horizontal doesn't really matter in that issue, except like I mentioned, a vertical antenna is very dependent on the ground. If you don't have a good ground, you're going to be at a disadvantage. And if you're in a residential area, you may have you may hear more man-made noise, because that's what man-made noise is, vertical. I would prefer a horizontal antenna if you can do it. Yep. Yeah. Yep. I know we're in a quiet area. We're on a little bit over 2 acres, kind of rural. And I had the fortune of comparing, I have a Tenedyne T6 6-element log P. It's not real big. It's equivalent to a 2-element monobander on each of the bands, 20, 17, 15, 12, and 10. And compared it to a Cushcraft R6000 vertical. And generally, noise wasn't the issue, just that the horizontal antenna ended up about an S unit stronger. That doesn't say anything bad about the vertical. You could still work DX on the vertical, no problem. But have a good ground system, and hopefully your noise isn't that bad. But I'd prefer a horizontal antenna.
Okay, I got a question.
Sure.
Oh, I'll make a comment about the vertical horizontal. I've got both, a big vertical, a lot of radials, and horizontal. And there are times when I work better with one or the other, and sometimes it makes no difference, whatever. But my question is about Korea, a little bit off, but is anybody licensed as an operator in Korea? Are they allowed to operate, or what's the chances of actually getting somebody in Korea?
Bill? Yeah, okay. Is there anybody licensed in Korea to do something? Bill or Glenn, can you guys answer that?
We got an update from W3UR, the Daily DX last February. and there's nobody licensed. It's not allowed. The Russians had actually made an overture once they started becoming friends, and they said no. So as of right now, it's just not going to happen. And that could change tomorrow, but for now, it's just not going to happen.
Okay, thank you, Bill.
Any other questions?
We depend upon ionization for our propagation. So I'm wondering what's the difference? What changes when we have these CMEs or coronal holes versus just regular ionization? What's
Okay.
the difference?
What happens when we have a CME or a coronal hole? What happens to the F2 region? It's all up in the F2 region. What it does is rearranges the ionization up there. So it moves it somewhere else. And that's generally why we see lower MUFs, because the ionization is moved. Now, remember I mentioned that a moderate spike you can see enhanced. Generally, that's because of the ionization at F2 region altitudes is moved down to the lower latitudes. So that's when the low latitude or mid latitude paths are improved if it's a small disturbance. But it's just how the winds are up there at the F2 region altitudes and how the ionization moves around.
Okay. What?
More than likely, okay, what's an ionoson, and is that little streak you see running across? Yeah, an ionoson is just basically a radar looking straight up. And it runs from about 2 megahertz to maybe 15 megahertz. And it, just varies 2 megahertz, 3, 4, 5, of course in smaller steps. And it's trying to see what frequencies are reflected back down to Earth. And we can determine what the ionosphere looks like, the F2 region and the E region, by looking at the ionoson data. And yes, if you're close enough to an ionoson, or if propagation's good enough, you can see an ionoson sweep across the HF bands. I don't think they cause any interference, right? Yeah, no. Who's or characterize the ionosphere? Ionospheric scientists, and they're usually associated with like schools or a government facility or something like that. And a lot of good information that comes out of it. And hopefully it'll allow us to better understand what's going on up there. But like I mentioned, there's not as many ionosons running as there used to be. That's unfortunate. I guess maybe.
Anybody else?
Yes, sir.
With the advent of artificial intelligence and the advancement of weather satellites, the information that we gather about the ionosphere, wouldn't that be closer to real-time knowledge than statistical predictions?
Well, okay. With the data we collect, doesn't that give us a real-time indication? Yes, it does. The ionoson, some of them run on 15-minute cadence. In other words, every 15 minutes they take data. Some run on 10 minutes. Some run on 5 minutes. So we get real-time ionosphere data, but we can't tie that to what those events in the we can see the events in the lower atmosphere causing, but we don't have anything to make a model yet of that. Like if a volcano erupts, what's the chance that it's big enough to start a gravity wave? What's the chance of that gravity wave propagating up to the F2 region to do something to the F2 region? And then what's the probability of what the F2 region looks like then? So that, yeah, we can get real-time data, but we just can't tie it to everything that we know about what causes it yet. Hopefully I explained that okay. I don't know. It's not yet until the ionospheric scientists can identify parameters from these events in the lower atmosphere. You know, we don't, you know, for solar, we have solar indices, right? We have K index, or I'm sorry, the K index, the A index, the solar flux, the sunspot number. So we have parameters. We don't have any parameters on what happens when a volcano, you know, happens, or when a hurricane happens, or we just don't know enough yet about it. I'm not sure we're going to see daily predictions in our lifetimes, but we'll get better and better slowly. It's unfortunate that solar cycles take 11 years. It'd be nice if they only went 1 year, you know, then we can maybe get there quicker, but solar cycles take too long. Well, just the solar minimum part, right? Okay.
Well, we can take one more question here.
Sure.
2 of 3 factors that we understand. What's the third that we don't understand?
The events in the lower atmosphere or at ground level and how they can change the F2 region. Yeah.
Okay, thank you, Carl.